Yep, seems like I'm live, and yeah, probably am live. Now, machine learning. Yesterday, what did we do? Page 300, I guess. We were at the exercises of chapter number 9, and we got stuck at a question, right? Which was, where is the work? And this question number 7. Yeah, 3D objects and this. So I can either go, let me go to the folder where I write the code, chapter 9. Yep. This is the code that I wrote yesterday. Either I can work on this or I can write new code from scratch. I think I will write new code from scratch for this, and I will comment out the old one here. And let me read the question again. 3D objects are often stored as an array of points. 3D objects are often stored as an array of array of points, where each point is a vector array. Each point is a vector array consisting of 4 values x, y, and z, and the constant 1, 0. Rotation, translation, and scaling and other operations are accomplished by multiplying each point by a 4 by 4 matrix. Each point has to be multiplied by a 4 by 4 matrix. Each point is contains 3 numbers, 3 values, and a constant. Okay, and the whole 3D object is represented as an array of three of a point, and a point contains 3 values x, y, z, and a constant. The following C code shows the data type and transformation operation. So a point is an array of float, and matrix is a 2 by 2 array of float, and float is 32-bit long. Right? Wrong. A float? Shit. A long is 32-bit long. A float the size in C float is 64-bit long. 4 bytes. Okay, it is 32-bit long float. 32-bit long, 4 bytes, 64-bit size. Uh, Type name 64-bit size and size of float. ZU this return 0. The float in is 32-bit. It follows the IEEE single precision format with a precision of 9 decimal places. Size of, okay, float is 32-bit. That is okay. So let's first do that. In the data section, I will define a point r. Right. So this is the function. And what does it do? It takes in two integers, initializes two integers, that will be done in a register, and it takes in a point. And to apply something to this point, I have to multiply the contents of this point, these 4 values, by the matrix. So this is just a matrix multiplication, a vector matrix multiplication. That is all it is. And then I have here a thing called result, which has the data type point. That is, it is an for array which contains float, and it contains 4 floats. Array of float with length 4. And now I will loop from I0 to 4, where I am first of all initializing the ith position in the result with 0.0 since it is float. Oh, since it is float, that is why this question is in chapter about floating point things. Okay, that makes more sense. And then I am iterating to fill that ith index in the result point, and at the end I am updating the original point with the result point. Okay, that should be simple enough. So here I will define my point, which will contain a word that is 32 bits long, and the point is this. Okay, we will just start normal, and the matrix will also contain word, and it will be 1, 2, 3 something. Okay, that is one row of the matrix. This is the next row of the matrix. This is the third row of the matrix, and this is the fourth row. Yep. Now we got that. Now in the text section, we will say we have a thing called globe. Our main function is global, so that it can be accessed from outside the file. And let's define the global thingy. First of all, I'll just store the frame pointer and the link register onto the stack so that I can get them afterwards at the end by pre-incrementing the stack. First, I will simply just get the values of the point and try to print them. First of all, that is my first goal. So I will get the address in the first zeroth register for the point label by first getting its page address and then adding to it the offset like that. Now I have the location, the address for the point, and now I would like to print it. How do I do that? First, I will get all the values from the point. Let's say store, not load pair. I will load into the 32 bits of first and second register. The address which is at zeroth register, the value whose address is in the zeroth register, and I will do the same for the next two values in the point and store them into the lower 32 bits of the third and fourth register. And also I will provide an offset of 8 because I used 8 values above, 8 bytes to store the above values, right? Yep, 8 bytes. And yep, now I would like to print it. To print it, I have to define a format string as keys, which will be let's say, oh shit, this got disconnected now, and like this. Then I will have a float, and 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 at the end a new line. And let's make these float 0.9, 0.5, 9.3, and 4.6. Right. Now I have the values, and now I want the address for the format string in the zeroth address. So fmt get the page address and add to it fmt page offset. All right. Now I need to get some space on the stack. Let's say how much? 48 bytes. would be okay. I only actually need 16 bytes, but okay, let's just use 16 bytes, 32 bytes, not be greedy, and store these values that I got onto the stack by store pair w1. That is the one that I want to store first, and then w2. Where do I want to store this? In the stack, at the top of the stack. Yes, this should work. And then store the pair w3 and w4 at the stack, but with an offset of 8. And after that, I can just call printf. And then I would like to get uh, pop the values from the stack to get back at the original place, and then load back the frame pointer and the link register from the stack, and then increment the stack by 16, and then just return with an exit value of 0. Clang chapter 9.s. Put the output in dot out, and okay, out of range literal value. Out of range literal value. Why is it out of range literal value? I did store some value with point here. See, here I stored 0.1. So why is it? Okay, so let me first just store them as decimal values, and after that I will try to print them. No, that is wrong. Or maybe that is wrong because I am printing them as float, I guess. And maybe this should work. Okay, 1 is correct, but then 9 and all that shit is not correct. That is wrong. Is it because I'm using 4 bytes to store a number there in point, right? That is correct. But then I am getting those values from the stack. Mhm. Okay, the first value that I got is 1, and the second value that I got is 9. So the thing could be that, this makes sense that I am getting the values as I want, but the printf function is after looking at one value, it the printf function is jumping up by 8 bytes, not by 4 bytes. So if I do this x, and if I also make all of this x and make this 16, this might work. 1294. Yep. Okay, so now we know that we can get the values as we want them. That was the problem with yesterday's program, right? Yep. Now I can get I got the values of the points. Yes, that is correct. Now, what do I want? I want to multiply this point with the matrix. So let me also get the address for the matrix and start storing the points from the second register instead of that. Okay, I want to get the address in the first register for matrix. I will get the page address first and then add to it matrix page offset. Now I have the address for the page, I would like to get the values, multiply them, and store them. But do I want to create a loop? Nah, this is just a 4 by 4 multiplication, so this would be much faster without a loop. So let me do this instead. The first values that I want to get, I will be using registers 6th, 7th, 8th, and 9th for my task. And let me get the values. LDP. Nope. I will have to load them individually because the first value that I want to load is this one, and then the value that I want to load is this, and I should remove the spaces because the spaces will also be stored there. I suppose then load into W, that is 64 32 bits. On the 6th register, the value whose address is in the first register, and then load in the 7th register, the value whose address is in the first register with an offset of 4 up, and then load into the 8th register the value, nope, not an offset of 4 but an offset of 4 plus 4 4 4 to get at the second element of the same row, then 4 again to get at the third, 4 again, now we are at 8 and 12 to get at the fourth, and then 16 to get at the first element of the second row. And here I have to give an offset of 16 16 32, uh, and then load into the 9th register, and the offset is 48 now. Yep, I have the values from the matrix. Now I want to multiply and store them, for which I will use MADD, MADD. And my destination register, which will store the result actually, will be spanning from register what? Let's say X 10th, from register 10th, register 10th, and multiply the contents of register second, which is the first value of the point, and the register 6th, and that is it. Do I want to add something to the first one? Nope. I can make this simple multiply, and the next one should be multiply and add, and I will store it into the 11th register, the product of the third and the 7th register, and add. Nope, this has to be stored in the 0th, in the 10th register, because multiplying a whole row with the point gives me only 1 value of the result. And store, add to them the contents of the 10th register, and do this again with the 4th and the 8th register, and add the contents of the 10th, and do it again with the 5th and the 9th register, and add the contents of the 10th register. That is crazy. Now I got the first value of the result probably at this point. Then I would like to store, before this I would like to add to the first register and store 4, so that I will get the second value, the second elements from every row. So I have given an offset of 4, and then the same, but this time with the 11th register. Yep, 11th, and yep, that was it. And the same again, same thing again. Now the offset has to be, yeah, 4. The offset is again 4 because I already increased by 4, and the total offset from the original would be 8 at this point. And here let me do 12 to store the third element of the result. And yup, yup, yup. Where did I go? Yup, here. And yep, again an offset of 4, so that now total offset is 12 to get the fourth element. And I will be using a register number 13 here. So my speed is getting slower. Now I have the result in register number 10th, 11th, 12th, and 13th. Now I have to store them onto the stack and print the answer. So I can change this to 10th, 12th, 13th, 13th, and 14th. And I should get the result actually. Okay. Invalid operand for instruction because I am using 32 bits for multiply. Okay, let me use the full capacity of the register. I can do %s replace. No. I have to do this manually because I only want the change to happen when I am multiplying, not when I am loading. Yep, that seems right. And now the last one. Yep, that does compile. Let's see the output, and that is the output. So let's see if we multiply that on our own in chapter 9.s 21. This is the thing that we are multiplying. Let's say instead of doing vector multiplication, we got this. So for the first value we have 1. Let me make some spaces so that I can actually see it properly, more clearly. And yep. So for the first value in the result, I have 1 multiplied by 1, which is 1 plus 2 multiplied by, shit, that is crazy, 2 multiplied by 1, 5, 2, 3, 4. Yep, and plus 9 multiplied by 2, 3, 4, 5 plus 4 multiplied by the number I can't even see. 4 multiplied by, let me copy this, multiplied by 2, 3, 4, 5. Okay, 4 multiplied by 3, 4, 5. The answer is 60. Oh shit. The answer is 60954. 60954. God damn it. Yes, it works. It works. And how much time did it take us? Okay, desktop is way over here somehow. Why do I have random new tab here? Wait, the things are not organized properly. Okay, it took us 24 minutes, about 25 minutes to do this, but we did this, got it. Oh yeah, we did this without loops in assembly, but not using loop part is bothering me a bit. But well, we did it anyways. Optimize the AArch64 assembly code you wrote in the previous exercise. Use vector mode if possible. Well, I have already written the optimized version by not using a loop, and this is not a spaghetti code because I'm not using a loop. This is crazy code. Very well optimized. If I use vector registers, then it will be more organized, but I do not know how I can use vector registers in here to do my bidding. And I don't know how to do that. That is crazy. So how can I use vector registers here? Well, I can do vector add. See here, vector add, vector multiply, but that would not be more optimized because they have not told me yet. In this book, it is not described how I can use vector multiplication or vector operations at multiple data points at the same time. Or the best that I can do is instead of using these here, I can use S, which should be well optimized, I guess. And here also, I will use single vector registers to do my bidding. S, and the result will also be stored. Not in a S, but in a D. Uh, yeah, S is fine. S is fine. S is fine. Single bit. Like S means single precision. Single precision is fine. Mm, mm, Update the values here. I'm changing all of the general purpose registers with vector registers, single precision. And I will also have to change the operations. Yes, I will also have to change the operations from multiply to f multiply and f add for floating point. Okay, the optimization I guess they want me to do is not in the terms that I can use. I can perform same operation on multiple data sets at the same time. I guess the optimization that they want me to do in this exercise concerns itself with the use of floating point registers so that I can with the use of floating point registers so that I get a better multiplication because they are more optimized for floating point operations. And here I don't think I can use a store pair with a single bit because they will be stored in a way that the printf function does not expect. So I will have to store them individually. Store this value and store S11 at this stack with an offset of 8, and then store S12 on the stack with an offset of 16, and then store S13 on the stack with an offset of 8, 16, 24, 24. And then, yeah, that should work. But yes, I also have to update. I also have to update these. The operations also need to be updated. Nope, not float. Float is nothing. F, F, and well, that much could have been done by. Okay, the answer is 0 because I am printing D here instead of F. Is that the reason? Okay, here I am getting the points correctly. Right, correctly. Let me print the points. 2 and 3 and then 4 and then 5. Wait, the points are not loading correctly. Here I load pair S2 and S3 at 0 from the point labels address, and then S4 and S5, and S means single precision, and I'm getting 0 instead of anything else. I'm getting 0. Let me comment all of this out. This might be maybe causing the problem. I don't know. Making a random changes to my code, expecting it to work. I'm printing flow. I guess the problem lies with this 1 point something number, 2 point something, and 3 point something, and 4 point something. Okay. Chapter 9. Let me ask ChatGPT. This part is giving me a problem. This part is giving me error and I am unable to store float single precision value in the data section. In AArch64, word is used to store 32-bit integer, not floating point values. Since you are working with float, I have to use dot. Okay. That was, I guess, stupid. So now I should not get any error, and it still doesn't work. Why? I loaded the values here. And how much space does the float take? Float takes 32-bit. Okay, that is okay. I am getting the values in single precision registers, single precision versions of registers, and then storing them onto the stack. Is it because printf expects something else? Let me use the normal W registers. Right, let's see how that works. in the general purpose registers. Does that uh, typo founded? Where was it? Yep, here. Make this a stack pointer. Lang add. Okay, the general purpose registers also don't work when getting the floating point value. Now I don't know where the error lies. Is there in when I'm trying to print them as float? Is that causing the error? Nope, that is not. That is not causing the error. Then what is it? Is it the offset? Does the offset has to be like this? When I'm storing one value, taking only the space that it actually needs and not padding it. That is also not the case. What if I change this to digit now? Chapter this. Okay, that was not causing the error. So if I have to use floating point here, and then the offset also needs to be 8 and 12, and then no, not 12, but 8, 16, and then 24. 16 and then 24. Yep. Okay, where is the problem? Here I got the address of the point, and then I loaded the values, and they do take 32-bit. Maybe they take more. I don't know. Maybe they take more bits than it says. Then this one should work. No, they don't take more than that because at this point I'm using the W register, the general purpose registers. So this should not cause any problem. I am getting 4 bytes from starting from the point address, and then I'm doing literally nothing, and then I am getting the address of the format string in the 0th register and getting some 32 bytes of storage onto the stack, and then I am storing and then I am storing the contents of registers onto the stack starting with the W2 register, general purpose register 2. Hmm. This should actually not cause any problem. Is it some, does there has to be some different way to store floating point values onto the stack? I guess. Let's see. After this, go down, in history, go down and, nope, not tab, but give some space. Yep, this code is not printing the value of the point. This code is not printing the value of the point. Yes, the issue in your code comes from how you are loading and passing float point values in ARM64. The key problems are this is loading 32-bit integers, not float point numbers. Okay, LDP, you need to use LDR instead of loading a single precision float point into float point registers. Incorrect usage of printf. Printf expects floating point arguments in floating point registers starting from S0, not W2, W3, etc. You should use float point registers like these S0, S1, etc. to pass floating point arguments. With that, okay, I should use individually load them. Okay, let me try to individually load them, not load them as a pair LDR, and I will be loading them the into these registers only, into these general purpose registers only. LDR W3 X0 with an offset of 4, and then LDR load the value of the fourth register with an offset of 8, and then load the value into the fifth register with an offset of 12. And then I'm storing them individually onto the stack. Let's see, maybe printf does not expect its. Yes, I guess maybe printf does not expect its arguments on the stack when it is float. Maybe it expects them to be in the float point registers. So move into S0 the value of S2, and move not the value of S2 but W2, and move into S1 the value of W3, and move into S2 the value of W4, and move into S3 value of W5. Invalid operand for instruction. Why? Single precision takes 32-bit to be stored. Let's. Is it F move? F F F F move. Is it F move? Land. Okay. It does compile. What do we see? We see the wrong results. Okay. Let me store them into these registers, and not even these, starting from 0, then 1, then 2, then 3. But then here I am overwriting those values, so let me delete that. Trying, it does compile, and the answer is wrong. So what did ChatGPT say? Okay, this we did, and we got the address in the 0th register for the print, and then it just says to print them, and that is what we are doing here. That is what we are doing here. Well, let me store onto the stack from these registers. 1 and S2 and S3. Okay, here I am loading the values into the floating point registers. There, I do not think can be any problem in this part. If this is correct, cannot be more correct. Then I'm getting the address for the print string from there. Then I'm getting 32-bit of storage, 32 bytes of storage on the stack, and then I am storing these values like so. And I see nothing. Let me change the offset, maybe like that. What is the offset given by ChatGPT? Has not provided any offset. It is not putting the values onto the stack, but I get 4.8 at some point. Let's see, do I have a value 4.8? Nope, not even close. 4.8 is not a value. Okay, but I did got something. So printf is taking its argument from the stack. That is a given. Single precision. Printf. Printf is taking its values from the stack, and this is still not printing anything. And ChatGPT does not know how to fix it. That is just crazy. I will have to fix it myself, which gives me more power. This still ain't working. Store 0 is unnecessary because this are already directed for passing. Well, misaligning sub-stack pointer 32 is unnecessary for passing floating point arguments since they got in registers. Well, me doing something unnecessary does not mean that I have that the necessary thing will stop working. Right. Yep. The necessary thing should not stop working. Yep, this should work. This should work. Yeah, mine's not working. It is just how things are in Mac. Let me get back to the original thing, how it was before I commented everything out. And yes, before I changed F and before I changed S. Yep. Oh, that must have taken some time doing all of that manually. Yep. Now our code should work and it does work. Okay. Now moving on. Hmm. Moving on. Question number 9.9, and then we have only one question remaining after this. Since the fourth element of this point is always 1, there is no need to actually store it. This will reduce memory requirements by about 25% and require one fewer multiply. The C code would look something like this. Okay, this takes only 4, 3. And here. After defining a result, I am making the result, the third row of result, directly equal to the matrix's third row. And then I am multiplying and adding them. And that makes sense, I guess. Yep, that makes sense. Write optimal RC neon code to implement this function. Yep, I got this. Chapter 9. So instead of here, I know that this is going to be 1, so I will not store it. And let's say that it is 1, and then here at this point I will only get a register, the fourth register, and here I am getting the values for the matrix row. Then in the start, let me initialize the registers that I will be working with. like the 10th register will be initialized to, I want to put it equal to, shit, yes, I have to load the value at from some point. Yes, load into the 32 bits of the 10th register the value from the last element of the first row, and that should be equal to 1 with an offset of 12. Yep. Then load into the 11th register the value with an offset of 12 plus 16, 28. Yep. And then load with an offset of 28 plus 16, 38, 44. And then load in the 13th register the value of the last element in the last row, which has an offset of 60. Yeah. And then I will continue do all of that, and this has to be not multipliable, mad with these but not with the last one, and I don't even have to get the last element like that. And here also I can remove this, yes, and I have to make this MADD and remove this and do 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 this and make this MADD and do this and do this MADD. Yep. And yeah, all of everything else will be as it is. And now I get error. Oh, in the first, then I have to give them when I'm using mad. Yep. That makes sense. Let me give them extend here, and that is the register that I want to add in the mad instruction. And this x13 is that correct? Chapter 9, I'm supposing. Okay, the answer should be 1. Let me make some space. 3, 4. 1, 2, 3, 4. Okay, the answer would be 2, 3, 4, 5. 2, 3, 4, 5 plus 1, simply 1 plus 1, 5, 2, 3, 4 into 2 plus 9 into 2, 3, 4, 5. 5, 5, 3, 9, 1, 9. And I guess that is the answer there. 5, 3, 5, 7, 9. Did I do something wrong? 1 into 1 is 1. Okay. And add to that this number multiplied by 2. Okay. 2, 3, 4, 5 is the last number. 2, 3, 4, 5. 2, 3, 4, 5. 2, 3, 4, 5 are the two last numbers. That is correct. So 2, 3, 4, 5 plus 2, 3, 4, 5 into 9 plus, right, plus 1, 5, 2, 3, 4 plus 1, 1, 5, 2, 3, 4 into 2 plus 1. That is even more wrong than before because I have to remove this 2. 53919. That is the same that I got before, but that is not the thing that my program is outputting. 2, 3. What if I remove this? Then I'm getting 51574. Is that the output of my program? 51579. The last one is always 1. So how am I coping with that? Okay. Yeah, okay. That makes sense. So the one for the first register has to have an offset of 10. Wait a minute. No, not an offset of 12. It has to have an offset of. I have to start storing. The 10th register will have the first element of the last row. Yes, the first element of the last row, which is 2, 3, 4, 5, and it should have an offset of 16 plus 16 plus 16, that is 48. Now, the second register should have the ah, 48 plus 4, 52. So the problem was with offset. It seems 50 and then 60. The last one should have been correct. And dot line out 53919. That is correct. If this function yet, yes. Battery is running out. Charger. Yep. So why is my desktop there? It's been 1 hour and we have only one question remaining. The function in the previous problem would typically be called multiple times to process an array of points. As in the following function, x formal takes in a matrix and a point and int num points I equals to this less than 1 num points x form for it will take multiple points. This could be somewhat inefficient. Rewrite this function in assembly so that the transformation of each point is done without restoring to a function call. Without resorting to a function call, make your code as efficient as possible. I have to write this code as efficient as possible. So I am already doing this much. I am already doing this much. What do I want to do? I will pass in the address of the point, the matrix, and am I using the third register anyway? Yep, I am using the second and the third register. So where will I put? Yeah, I don't have to do this here. I will do this inside the function. I will get the point inside the function itself, and yeah, and I will put the number move, let's say, in register number X. What are the registers that I am using? From X, 10, 11, 12, 13 is the last one, right? I can, 14 is the last one, right? Why do I have a register 14? Why is this not 11? Why is this not 11? 11, 12, 13. In chapter 9, the problem here, remove that and do it again. Okay, the first one is correct. Let me check the last one. 2, 2, 3, 8, 2. In chapter 9, for the last one, I have to multiply I have to add 5 plus 2 into 5, 10 plus 9 into plus 9 into 2435, 2435, yep, and add the last thing. What is the last thing? The last thing is 452. Add 452. The answer is 22382, which is correct. Now it is correct. Okay, so I have the 14th register empty. I can pass in the number in the 14th register. After getting all of both of these, move in the 14th register the number of points that I have. Let's say I have 5 points. 5 points is quite a bit of number. And then the next point begins, and then the next point, each point will have only 3 values, and then the next point I have 1, 2, 3, 4 points. This is the last point. Yep, that is the last point. And after that, after doing that, moving this, I would like to call the matrix multiply function, or maybe I can just start a loop from here. Start, call this loop. Right, inside the loop I will do this, but before that I have to see the value of point. Hmm. I wanted to see the value of point. Nope. I will have to give when I'm getting these values. Before getting them, I have to store the address at some point. I will be getting an address every time, and I will be giving them a. Okay, let me move number 5, that is the number of points that I have, into a different register so that I can compare that counter with the contents of the 14th register and start looping back, and also give um, a offset to the 0th register. Right, I will move into the 15th register the content of the 14th register. Yes, after getting the address, I will add to the 0th register the value in the 15th register with the logical shift left of. I have to multiply it by 4 by 4 by 4 plus 4. 1 would mean 16, 2 would mean 32, and 3 would mean 48. So I have to multiply the number by 16. Multiplying by 16 means left shifting by 4. Yeah, and add to it. Okay, and after adding, increment the 15th register x. In, increment the 15th register by 1. Yep. Is this much correct? Yep, this much seems correct. Yep, totally seems correct. At the end, after printing, After printing, I will loop back. How? After printing, I will compare the 15th and the 14th register and branch to the loop if 14th register becomes equal to 5. If not equal, if less than, if 15th is less than 14th, then I will branch to loop. Logical shift left, that seems to be a problem. That is not even the correct format to add anything to something. Here, I have to provide a destination register. That is wrong. Because I started adding. Okay, I have to clear the stack, not by moving away the stack pointer, but by actually putting in zeros in the places that I want to store. So after getting some space on the stack, I will do. And why is this not printing multiple times? I am looping only after the print statement, so I should see things being printed multiple times. Store xzr and xzr onto the stack like that, and again store xzr, that is the zeroth register, the register which contains the value 0 simply, and then I will replace. Well, nah, I'm not adding, I'm only storing, so that was stupid. What's that out? Why is it like this? Okay, because I am not reinitializing, I'm adding and okay. That is stupid here. Move to the 15th register 0. And also I have to initialize registers. The answer is okay, yeah. This also needs to have an offset. Not like this. Yep. This also needs to have an offset. No, this does not need to have an offset. This is totally fine. Yes, before this, I will put 0 in the whole register and then move something there. Move into the 10th register 0 and move into the 11th register 0 and move into the 12th register 0 and move into the 13th register 0. Okay, I get the answer for the first one, which is correct. The correct answer for the first point, but not for the later ones. Why did the loop end? I'm starting the loop at 15 equals 0 and 14 is equal to 5. And since they are volatile registers, they are being overwritten by the printf function. So I have to store them onto the stack. For that, what do? We'll get some space on the stack, let's say 16 bytes, and then I will store the values of store pair 19th and 20th register onto the stack and use 19th here and 20th register here. And yes, I can do this. This something like this, x15 will be replaced by x20 globally. and same for x19. So this percentage s comma x19 will be replaced by not x19, but x14 will be replaced by x19 on every line that it appears globally. Oh, there is only one place that it appears at. Slang. Oh, this should work. And segmentation fault. The first one is correct. Okay, maybe the offset went too far. I guess I should remove the spaces. Those might be causing some problem. I guess, but they are not causing any problem. The first one got multiplied just fine. Segmentation fault. Segmentation fault when I am loading. And this seems correct. This is, cannot be causing any segmentation fault. Here I'm getting the address of the page here and adding to the zero the address, the content of the port with an offset of, after logical left shifting it by 4 times. Okay, I have one. If I logically left shift it once, I get 2. If I left shift it again, I get 8. If I left shift it again, how many times? 1, 2, 3, 4, 4 times. um, then I get 16. And if I have 2, I do not have if I have 2, 2 multiplied by 16. If I have 2, if I left shift it once, I get 4, then I get 8, then I get 16, and then I get 32. Which is correct. Which is correct. 32 is also. Is it correct? Offset of 32. Okay, let's move on to number 3. If I get 3, that is 1 and 1. If I left shift it once, okay, and that would be the sum of 16 plus 32, and that is 48. So yeah, that is correct. That is what I want. And now multiply it by 16, because 6, that is how much a point. No, that is not how much a point has. A point takes 12 bytes, not 16. So I have to multiply that value by 12. And to multiply something by 12, I actually have to multiply it by 12. And I will store it in it's a 14th register. So mul and store in the 14th register the contents of 20 and 12. And here I will use 12th register, 14th register to give an offset. Valid operation for instruction. I cannot multiply with an immediate value. I have to have that value somewhere stored. Multiply. Okay, so let me move into the 15th register, 12, and here use x15 for my purposes. Segmentation fault. The first part is going correctly. The first point is being multiplied correctly. And when I get to 1, I will add to x an offset of 12 so that it will start at 23, right? And I am getting the address of point. Yep, I am getting the address of point, and then I am adding to that base address the offset 12. And also, yep, at the end, after the loop, I have to reverse this stuff, right? But that cannot be causing any problem after the loop. Yep. Sub, instead of sub, here I will do add to pop from the stack, and here I will do ld load pair these values from the stack, and no, here I will add afterwards. First I will get the value and then do this. This should not be causing any problem, but these is causing some segmentation fault. Why? So I know that the second loop began, right? The second loop did begin, right? I have in the 20th register. Here I am messing up with the 20th register and adding 1 to 0, which is a crazy thing for anyone, any human to attempt. Then after adding that, I'm comparing the 20th register with the 19th, and then I'm moving back up to the loop. And at the loop, I am getting the address of the point, base point in the 0th register, and then I'm multiplying, moving 12 to 15th, and I'm multiplying the value in the 20th register, which is 1 by 12, thus getting 12 in the 14th register, and then I'm adding for 12 into the base to the base address in 0 to get, oh, no, yeah, I have to multiply by 6, right? 6, because I'm using 12 nibbles, not 12 bytes. I'm using 12 half bytes, and the base address has to be incremented in terms of byte, how many bytes I'm using. And in total I am using how many bytes? Half byte for that. Why did I even get to the number 12? That is just crazy. Yeah, point takes up 4 and wait. Yeah, a point takes 4 bytes, and 4 bytes. Yes, it does take bytes. I am hallucinating, am I? No. 4 bytes, yes. A point takes 12, 12, 4 bytes for one value, then 4 bytes for the next value, and then 4 bytes for the third value. And in total, it takes 12 bytes. Right? Right. So I have to update by 12. Maybe this I can do. Instead of storing the index here, I can store the total offset, and the total offset would be, since I have 5 pointers, 5 points here. Let me do just let me just have 2 points here instead of 5. So when I have only 2 points, these two and that two, I know the last offset is going to be 12, and so I can give this a value of, let's say, 14, and start this at 0, and instead of doing all of this, I can add the contents of the 20th register directly, and here add to it 12. Now what is the problem? Um, is there any problem? The color of things really are, why is it all white? There seems to be some problem. No, file segmentation fault, and the first one did work, by the way. Why am I getting a segmentation fault for the next point? Next time the offset becomes 12. What if I start with that? What if I start with 12? I do get something. Is that the correct thing? The question is that. So to get the answer, I have to, let's find out the answer for the first string. For the first value, which should be equal to 23 multiplied by 23 multiplied by 1, which is just 23, plus 324 multiplied by 1, 5, 2, 3, 4, right? 1, 5, 2, 3, 4, yep, that seems to be it. And then 512 multiply. No, not multiply, but I have to add these two. 512 multiplied by 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 5. Yep, plus the last value, whatever it is. What is the last value? Last 2, 3, 4, 5. Yes, of course it is 2, 3, 4, 5. 2, 2, 3, 4, 5. The answer is 6138824. Is that what I got? I got 6138824. Yep, that is what I got. So why is this working here for the first time and then not working afterwards? I am adding 12. Here I started this with 12. I have to start with an index of 0. Which part is causing the segmentation fault? Which load operation or what? Okay, here this happens. Right, right, yeah, right. Yep, this happens. Is it when the second loop starts, there is some mishappening? Segmentation fault. I am trying to access something that I should not. Are there some? Yes, of course. Yes, of course, because I am inside the loop. I am loading from the 0th register, and I am getting the reinitializing this, but since I am calling printf during the function, the first register, which I am also using to load and store a bunch of values, is getting overwritten. So I do this. This should work. Let's slash out. Is this the same that I got before? Nope, this is different from what I got before. And wait a minute. Now it is working. Now we are actually getting somewhere. Why is my desktop coming here again and again? Because of the calculator. I'm calling calculator, and that is why. Yep. Now, hmm, 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 hmm. Now we are getting somewhere. This time, the error. Where does the error lie? Lie. I'm getting this. Okay. And yeah. Yeah. Hmm, 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 hmm. It should have worked. What are the registers that I am using during this? The registers are registers 0, 2, 3, 4, which I am loading at the start of every loop. So that should not cause a problem. Then I am using the first register, of course, and zeroth register is also being loaded, and first is also being loaded with the new values, and 10 to 13 are also being loaded with the new values. And I am also loading the 6, 7, 8th registers, and adding, multiplying, loading the new values here, here, here. 6, 7, 8. Hmm. This should not cause any problem, but it is causing some problem. I am reinitializing all the registers, right? Yep, I am reinitializing all the registers. Then why am I facing problems? And at the end, I am getting this, and then this. The stack pointer is also being messed up. But I do restore the stack pointer. Is it because the values in the stack pointer I have to store 0 maybe? Let's see, this might be very stupid. 0 and XZR 0 to override the values that I stored earlier in the stack pointer. But that does not seem like a good thing to do for any human being, because nah, this is probably not going to be the thing that makes this work. But anyway, oh, typo, typo. Yep, it wasn't supposed to work. Hmm. Why? Why is that? I'm storing 3 values here, just so, and then I am getting 3 values, just so. Let me print the points instead of this. Let me do with the second register that stores a value from the point. The third, the fourth register. No, here will come, the fourth will come here, and here the fifth. Let's out. Do I get the correct values? I do get the correct values. So wait, no, I do not. Um, I do not get the correct. I do get the correct value for the first three and first three in both the points, but when did I change the fifth register? The fifth, find x5, x5, capital N, x5. Yep, that is the only time I am using the x5 register. Or find w5, find w5. Yep, seems up, not wf, w5. Okay, not using it anymore in the current part of the code. I'm not using it. That is being overwritten probably by the printf function, right? Some garbage value by the printf function. I seem to see the thing here. Here I am. Num 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 num. That is just fine. That is absolutely just fine. I'm getting the values in 678, 678, 678. Sixth, seventh, and eighth register. They should. What should they give me? Matrix? Why am I loading them twice to get the new rows? Why only three? Because that is all I need. 6, 7, 8. Let me see the values of those. X6, X7, X8, X7, X8. I should see the same output, and I do see the same output, but that is horrible. That is not correct. 555. That, oh, no, that is actually correct. That is actually correct. Hmm, maybe. Fucking hell, this is the correct answer. Is this? Fuck, 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 fuck. The one time that we printed. Right. This is the correct answer. Why the fuck am I being? Ah, this is the correct answer. So we completed this chapter and we were getting the correct answer, but I thought that it is wrong and I don't know what the heck I was trying to fix there, but it works. Let me give it some more points. Yep. Now, how many points do I have? I have 5 points. Let me increase this from 14 to 5 into 14. What is 5 into 14? Wait, I can do, instead of this, I can go just put 5 here and this here, and instead of adding 20th register, I can do move value into the 15th register or 14th register, the value 12, and multiply and save in the 15th register the contents of the 4th, 14th, and the 20th register, and here add the 15th register and always given offset of 1. Yeah, yes, es funktioniert. advanced SIMD instructions. And how much time do we have? 30 minutes. We got this. Not the whole chapter, but quite a bit of it, I guess. Advanced SIMD instructions. In addition to the FP Neon instructions described in the previous chapter, AArch64 also supports advanced SIMD instructions which allow the programmer to treat FP neon registers as vector arrays of data. Advanced SIMD uses the same set of registers described in chapter 9 but adds new views to provide the ability to access the registers in more ways. Advanced SIMD adds about 125 instructions and pseudo instructions to support not only floating point but also integer and fixed point. A single advanced SIMD instruction can operate up to 128 bits, which may represent multiple integer, fixed point, or floating point numbers. For example, if two of the 128-bit registers, each containing eight 16-bit integers, then an advanced SIMD instruction can add all eight integers from one register to the corresponding integer in the original register, resulting in eight simultaneous additions. For certain applications, this vector architecture can result in extremely fast and efficient implementations. Advanced SIMD is particularly useful at handling streaming videos and audio, but also can give very good performance on floating point intensive tasks. I will have to get the charger. The stream is not stuck, right? Yes, it is not. Yep. The 32-bit FP Neon Advanced SIMD registers, originally introduced in Chapter 9, can be accessed using various views. Can the 32 Neon Advanced SIMD instructions, originally introduced in Chapter 9, can be accessed using various views. Some SIMD instructions use the byte, half word, word, and double word views from Chapter 9, but most of them use the advanced SIMD views. Figure 10.1 shows the different ways of viewing. Okay, there are multiple ways that we can look at an SIMD, advanced SIMD register, it seems. Each register can be viewed as containing a vector 2, 4, 8, 6, 8, or 16 elements, all of the same size and type. Individual elements of each vector can also be accessed by some instructions. The scalar register names and views introduced in chapter 9 are also the scalar register names and views introduced in chapter 9 are also used by some instructions. A scalar can be 8 bits, 16 bits, 32 bits, or 64 bits. The instruction syntax is extended to refer to elements of a vector register by using an index x. A scalar can be this many bits. The instruction syntax is extended to refer to the elements of a vector register by using an index x. We can refer to an element in the vector register by using an index x. Okay, for example, this 4s is element x in register vm, where vm is m is the number and v means vector, and 4s means this register has four single precision values, and a single precision value takes 32 bits and four of them takes 128 bit. So the whole register is filled, and x might mean which one of that register, where VM is treated as a vector of four single word 32-bit elements. That makes sense. Instruction syntax. The syntax of advanced SIMD instructions can be described using an extension of the notation used throughout this book. Each instruction operation of certain types of registers and their I'm losing touch with. The syntax of advanced SIMD instructions can be described using an extension of the notation used throughout this book. Okay, each instruction operates on certain types of registers, and there are many registers. Yes, advanced SIMD instruction syntax may use any of the following register definitions. Well, This is how we access registers, and here are the register definitions. Okay, let's see how we access the registers. Bn bit and the number of register, hn half single, and the number of the register, dn, when we are using something like this, and dn is this, dn double, and then the number of the register. And here we are using a vn to store 8 bytes, 0 1 2 3 4 5 6 7 8. And here is how we can access individual byte, vn dot 8 byte, and among those the vn register will store 8 bytes. 8 bytes will take 8 bytes of storage, of course, and among those 8 bytes we can access individual byte like this. That is crazy. And here vn stores 2 single bytes, and these can be accessed by a bracket, and then like this, like so, like so. And 4.5 bytes can be accessed like so. And if we are using storing 16 bytes, then those can be accessed like so. Okay, that makes quite a bit of sense. Now here are the ways that we can refer to registers. XY, general purpose. Yep, integer registers. WY all refers to 32-bit architecture integer register. And BY, BY means byte, refers to lower byte or byte of an advanced SIMD register, half byte of an advanced SIMD register, single byte that is 32-bit, and double byte that is 64-bit, and floating byte, which is how much bits, how much bytes, is used to indicate either a single word or a double word. Opinion register. S F must be either S for a single word register, D for a double word. Okay, instead of F, we can use S or D for single word and for single and double word. Then we can use VY to refer to a whole to the whole 128 bits in an advanced SIMD instruction, and V dot T, 128-bit advanced SIMD register treated as a vector of elements of type T. Okay, where T may be one of B, H, S, and D. Some of the instructions can allow a subset of these types. Huh. Huh. And that is what it means here. When I put a dot, that means after this is specified how I want to use this VN register. And if I'm using this notation, then I can access those individually. Yes, those divisions individually, starting from 0 till the end one, till the last one. Each instruction has its own set of restrictions on legal values for the registers and types used. Okay, let me write a bit of it. Let's say I want to use the fifth vector register with 16 bytes, 16B, and I want to get the fifth byte. So this is how it will be. V5 means I want to access the fifth advanced SIMD register, and then dot 16B means divide that 128-bit register into 16 individual bytes, and among those 16 individual bytes I want to access the byte at the fifth index location, and the bytes start indexing at 0 indexed. So this is the way. Okay, for example, one possible form of the move instruction is this: move w is 32 bits into tn, where t What does T has to be? T has to be a 32-bit value that is a single, which indicates that a 32-bit AArch64 register, normal register, is used as the source operand, and any element of any advanced register may be used in the destination. However, the instruction further requires that T must either be 2s or 4s, or in order to match the size of WN. Yep, 2s or 4s to match the size of WN. So, yep. Now, instructions may have several forms. In those cases, the following syntax is used to specify the possible forms. Instructions have several forms. Okay, so this is just explaining how the notation is going to be. Okay, option and braces around a string indicate that the string is optional. Okay, for example, several operations optimal r have an optimal r, which indicates that the result is rounded instead of truncated. Hmm. Yeah, and SU means either S or U. Parentheses indicate a choice between two or more possible characters or strings separated by a pipe. This character. Yep. And TN means a register number will come here. A string inside this symbol indicates a choice or a special syntax that is too complex to be easily described using the parentheses. This and is described in the following text. Okay, it is also it is also used to define a syntactical token when simply using a character would lead to confusion. And this is just a token. Okay, and how much battery do I have? That is 19. That is too low for me to be comfortable. Let me get the charger. The camera stopped working. Shit. Why did that happen? Shit. How do I? Fuck. Um, why did it got disconnected? I have to close. Wait. Let me make hide this for a bit and let me test things. Wait. Yes, you cannot see my screen. Let me check a few things. FaceTime. Yeah. Shit. It is still not working. Is it because my Wi-Fi is not the same as my phone's Wi-Fi? Nope, they are the same. I don't have Bluetooth on my phone. Nope, that is not the case. Shit, because my phone requires some update, or my laptop, yeah, my laptop requires some update. So that is why my phone's camera stopped working. So let me make this viewable again and change the screen. Was shit, I did make some screen. No, not that. Uh, shit. Okay, I guess that is how you'll have to do with this video without my face. Like, okay, that is totally okay. And let me get the charger for now. Yo. And I just realized that I was goddamn babbling till now. And now you guys cannot see my screen because my laptop needs some update. And without the update, it cannot connect with my phone as a camera. So, and we only have to stream for 10 more minutes. So, this is okay, I guess. The following function definition are used in describing the effects of many instructions. This is a floor division so that the decimal part of any number is removed. Nope. I get the highest integer and the highest integer that is lower than x, right? Maps real number to the next smallest integer. Yep. And this gives me the saturate function limits the value of x to the highest or lowest value that can be stored in the destination register. Limits the value of the x to the highest or lowest value that can be stored in a register. Saturation is a method used to prevent overflow. Okay, so if a value exceeds the um, capacity of a register, then it will become equal to the maximum limit of that register. Okay, then the register is saturated. In this, the round function maps a real number x to the nearest integer. The narrow function reduces a 2n bit number to an n bit number by taking the n least significant bits. That is crazy. This extend function extends converts an n bit number to an 2n bit number, performing zero extension of the number is if the number is unsigned, or sign extension if the number is signed. Yep, that also makes sense. Load and store instructions. How I can load and store. Let's see those. These instructions can be used to perform interleaving of data when structured data is loaded or stored. Hmm. The data should be properly aligned for best performance. These instructions are very useful for common multimedia data types because in multimedia data types we deal with pixels, things called pixels, which are a vector of values. Okay, and thus we can perform multiple instructions at the same time on mm, same instruction on multiple data points at the same time. Since pixel is a vector, so that is helpful for us. For example, image data is typically stored in arrays of pixels where each pixel is a small data structure, such as the pixel structure shown in listing 5.3.9. Okay, that was in chapter 5, that is too far behind. Since each pixel is 3 bytes and a D register is 8 bytes, since each pixel is 3 bytes, yes, 3 bytes. 3 bytes, isn't that too small? Um, each pixel, because one value is 1 byte long in a pixel, and yes. Therefore, and a pixel has three values which are 1 byte long. So in total, a pixel takes up 3 bytes, and a D register is 8 bytes. A D register is 8 bytes. D double register is 8 bytes. Loading a single pixel into a register would be inefficient. Yep. It would be much better to load multiple pixels at once, but even an an even number of pixels will not fit in a register. It will take three double words or quad words registers. An even number of pixels will not fit in because one pixel takes 3 bytes. So an even amount of pixel, two pixels will take 6 bytes, and even amount of pixels will take a multiple of 6. Therefore, it will take three double words. Yep. And or quadruple words register to hold even an even number of pixels without wasting space, as shown in Figure 10.2. Here, here. This is, yeah, this is how we can store them, starting from 0, 0, then 1, 1, then 2, 2, 3, 4, 5, and 6 and 7. Yes, many image. This is the way data would be loaded using an advanced SIMD LDR load instruction. Many image processing operations work best if color channel is processed separately. If each color channel, huh, color is also called a channel, is processed separately, so that red is processed separately, then blue and then green. The SIMD load and store instructions can be used to, if you guys can see the screen, right? Yep. Uh, yeah, and pixel data re-interleaved three double bit registers, double byte registers. Okay, that is also a cool way to store them. Instead of storing them like that, uh, one pixel in one register, then the next pixel, and then the next, I can store them like this. All the reds from eight, 1, 2, 3, yep, all the values for the red, uh, all the red values from eight different pixels will be stored in a single register, and all the green values will be stored in a different register, and all the blue ones will be stored in a different register. Okay, because it is better to process them separately. Each channel, it is called a channel, and each channel, if it is processed separately, then it is a good thing somehow. The SIM reload and store instructions can be used to split the image data into color channels like this, where each channel is stored in a different register as shown in this. Yep, like that. Each channel is stored in a different register. Other examples of interleaved data include stereo audio, okay, which has two channels, left and right, which is two interleaved channels, and surround sound. Okay, that is it three interleaved channels, which may have up to nine interleaved red channels. That is crazy. A 3D audio can have up to nine interleaved channels. That is crazy. Is the wait, let me first complete this. In all of these cases, most processing operators are simplified when the data is separated into interleaved channels. Um, how many channels does um, Dolby Atmos have? 64 channels of audio in mechanical theaters. That is just crazy. 64 channels. That is 64 different inputs, streams of audio. That is crazy. Dolby Atmos documentation. Dolby Professional. Okay. This is a image. This is an SVG. Huh. They have an SVG here for this. What is Dolby Atmos? Dolby Atmos is an immersive audio format that provides a compelling listener experience by surrounding the listener with sound. In addition to the additional 5.1 or 7.1 surround setups, Atmos Atmos introduces high channels to enable sound from above to increase aural envelopment. These are represented by the 4 at the end of 7.1.4. Okay, that is crazy. It has 64 channels. And now I guess we have done till here, and tomorrow we will start from here. Advanced SIMD load and store instructions. Load and store and Why is the n optional somehow? Option must be one of LDR. Oh, n means number like that. Okay. Okay, we will get into this tomorrow. And for today, that is it for the stream.